All right, so today we're going to be looking at section 1.4, function operations. I've given us two example functions that we're going to use to illustrate this. Function operations, so that means we're going to be adding, subtracting, multiplying, and dividing functions. And then after that, we're going to be doing a thing called composition of functions. We're going to use these two functions right here. And I'm going to illustrate to you the addition process. And then I have to illustrate also a function notation that this book uses and other books use. I don't care for it too much, but it's there. So let's start with addition. What I want to do is I want to basically create a new function, which is the sum of these two functions. So what is f of x plus g of x? Is really what I want to know. So here they've written it in function notation, and it means to literally replace these functions with what they represent. So, and then when you do so, please use parentheses around the functions. You can remove them once you see what it looks like using the proper order of operations and such like that for signs and issues, but always put them in parentheses. Don't just write them blankly. So this right here is f, so I would write 2x minus 1 plus, and then g is x squared. If you write it like this, you'll usually avoid a lot of issues that a lot of people have, okay? So then what do? Well, do I need the parentheses by properties of mathematics, like any minus signs in front, anything like that I got to worry about? If the answer is no, then just simply reorganize, combine like terms, and put it in the proper descending order, which means x squared first, then the 2x minus 1, and that is your answer. It is literally that simple. Now, the other notation that they use for this, actually, wait, let's go through all this first. So let's look at the subtraction. So I can do this a lot of different ways. I'll just do the same two functions. This time, you know what? I'm going to do it backwards. Let's do g of x minus f of x. So this here will illustrate why you need to put it in parentheses. Well, g of x is x squared, and then minus, and then f of x, like so. So if you can't see why, you can see that if I didn't put the parentheses around this, you'll see that I'm going to make a sign error. Because with the parentheses here, this negative sign, this minus sign out front is going to distribute throughout that. And again, put it in the proper descending order. Minus 2x, and then the negative times the negative 1 is a positive 1. And there is that one. How do I multiply? Well, to multiply two things, let's just go ahead and do it this way. They'll do it, and they'll write a multiplication, usually with a dot, or they'll just put them next to each other. So this means f of x times g of x. And again, you want to use parentheses so that you do it properly. Without the parentheses, you can use, most people make a mistake. F of x, 2x minus 1, times x squared. So as you look at this, I hope you notice that this is a binomial times a single one. And so this is just a distributive property. Right, so multiply it out. X squared times 2x is 2x to the third. X squared times that is minus x squared. And so that would be the answer for that. Just multiply them together. So what about division? Let's just do f of x divided by g of x. Just like so. Again, even though you don't necessarily need it, I do recommend highly that you use parentheses. You can remove them later if they serve no purpose other than at all, so you just get rid of them. So that's f, and that is g. The reason why I like the parentheses here, and you can make a side note to yourself, is the biggest error people make when they do this is they try to reduce. And you need to remember that you cannot reduce values. You cannot go inside a parenthesis and reduce. You can only reduce if you have all multiplication only. Like some people want to take this x and reduce it out with the x squared. But you can't, because inside the parentheses, this is not a multiplication. There is a subtraction sitting here. And you cannot reduce in subtraction. You can only reduce if it's all multiplication. Only factors can reduce, not a term. So you need to, the parentheses help you remember that. There is nothing that can reduce here. This is literally done. So you can just drop the parentheses and just write it as 2x minus 1 over x squared. There's nothing that you can do to simplify this. This is it. So all of those are how it's done. Okay. Now, all of these will also ask us to find its domain. So let's talk about the domains now. Okay. Operational wise, this is how it's done. I'm pretty sure it's fairly simple for you to see. Probably no issues or questions about that part. Okay. But the next part is, well, what's the domain of these things? And that's key. And this is what's going to be asked on your tests and stuff. Add the functions, identify the domain. So, to do the domain of each of these operational, new functions that you are creating by these operations, you have to first know the domain of each of the pieces that you are adding, subtracting, multiplying, or dividing. So go up here, look at this function. What is the domain of f? The domain of f, and I'm going to put a little tiny f here. You may not be able to see it in the video, but the domain of f, that's what that little mark right here is. What is the domain of this function? Well, this is a line, and its domain is all the real numbers. Okay? And so likewise, we go over to the piece that's called g. What is the domain on g? And we see that this is a quadratic, a parabola. And we know that this graph right here from our parent function, because this is one of them, that this domain is, again, all the real numbers. Which makes our life really good, because if I have a domain of all real numbers added to a domain of all real numbers, my answer's domain would be what? All the real numbers. There's no restrictions on it, right? If there's no restrictions on the parent functions, there's going to be no restrictions on the sum. Likewise for the subtraction. There's no restrictions here, so there's no restrictions here. This domain is also all the real numbers. The same thing with multiplication. If the two pieces I'm multiplying have a domain of all real numbers, there are no restrictions, so then the domain of this is also all real numbers. And then we get to this one. Well, the domain is the pieces are all real numbers, right? But when I divide them, what did I create? I created a fraction, didn't I? By creating the fraction with an x in the bottom, you have restricted the domain of the answer. The function f has no restrictions. The function g by itself has no restrictions, but g went to the bottom of the fraction. Since g is in the bottom of the fraction, there is a value that can never be in the bottom of a fraction, and that number is 0. Okay? So what value in g makes this 0? That number can no longer be in there. So this domain has a restriction. It is all the real numbers, but the x cannot equal 0. So you have to look at the domain of each piece that creates the new function, and also the domain of the new function. And put all those pieces together to find the most restricted domain. In this case, it's just one letter, it does not come out. If I did this other example, where I've put g of x over f of x, how does that change? Well, now I have x squared on top, 2x minus 1 on the bottom. Again, g is all real numbers, f is all real numbers, but when I divide them, the bottom can never be 0, and the value of x that makes the bottom here 0, all the real numbers, let's write it better, right? The x cannot equal, well, what will make that 0 would be positive 1/2. So it'll be all the real numbers, but x cannot be 1/2. In interval notation, I forgot to write interval notation. This would be a negative infinity to 0 joined with 0 to positive infinity. And then this one down here would be negative infinity to 1/2 joined with 1/2 to positive infinity. So that's how you eliminate just one value. This is interval notation. Either one of these phrases is fine for me in this class. So that is adding, subtracting, multiplying, and dividing, and the domains of such. The next one we want to talk about is I want to talk about composition. Composition is pretty much, it's just a substitution technique. Okay? And, oh, I forgot to mention the different ways you write it. Here's the alternate notation. Let me do that. Let me backtrack. Let's get this done. So this is the way I prefer to write function addition. The textbook will use, and some textbooks will use this notation, and it means exactly the same thing. Here I'm looking at individual functions that I am adding. Here, they're telling you to add the two functions to create a new function of x. This notation is, the function name is a new name called f plus g, and this is the of x. Just like right here, this is f of x. It does not mean f times x. This does not mean this times x either. This is a function name called f plus g and the variable x. This is f plus g of x. That's what this means. Please do not confuse it. This is not a multiplication. Okay, this is not a distributive property. This is not an x tacked on to the end that I multiply later. Okay, it is just a notation that means exactly the same as this. So what I usually recommend people do is, if you see this notation, to rewrite it as this notation, and then do the problem. It solidifies it in your mind. That is my recommendation. This one, because I wrote it this way, would be g minus f of x. That's the notation that represents that one. This one is written f times g of x. And this one would be f divided by g of x. So this notation means that notation. I recommend, again, highly, that you rewrite it into this notation before you continue. And again, this does not mean to times it. We did not times this thing. This is the name of the new function right here. And this new function comes from the division of these two functions. So that's the idea behind it here, okay? If you have any confusion about that later, please come and bring it to my attention. It's better that we take care of that now, all right? Composition, same thing. They have two ways of writing it. This is the way that some people use. I don't prefer this one, but it is used quite often. And it is composition. They use a little tiny, like, open circle right in the middle. It's not a dot. It's not an O, so it's not going to be fog. It's an F composed with G. It's just a little open circle like that of X. Again, function notation, variable of function. F composed with G of X. This is one way of writing it. I prefer this method. F of G of X. And I guess why I like this one, because I can see clearly that G is an inside function. See, I have an inside function and an outside function. And G is the inside function. It makes it a lot easier. Remember, composition is really just substitution. So I'm going to show you this with the two functions we had at the top. So what is f of g of x? Well, since g is the inside function, I'm going to replace it with what it is equal to. G of x equals x squared, right? G of x equals x squared. So I just substituted x squared for g of x. That's all I need to do. Well, now what? Well, now I take that quantity and I put it into the function f for its variable. I recommend you do it this way to avoid issues. Don't try and simplify it in your head. Actually write the function f, 2 times the quantity minus 1, and that's how you should think of it, 2 times something minus 1. And write 2 times something minus 1. Put an open parenthesis here. Replace the variable with a parenthesis like this, an open parenthesis. Okay? And then all I have to do is replace and plug in that x squared. It's that simple. It's substitution. Then I look at this and I say, okay, is there any sign issues I need to worry about mathematically? What does this become? This becomes 2x squared minus 1. And that is the composition. So what about the domain of this? So the domain of this is a little bit more tricky, and I'll explain a little bit more illustration here in just a moment. But really what I need to do is I need to, again, find the domain of each individual function. So I need to know what the domain of G is, and I need to know what the domain of F is. Okay? You have to start with G. G is the inside function. You start there. And what I'm looking for with G is I need to know not only the numbers I can plug in, so the domain of G, but I also want to know what kind of answers I get from G. So what's the range also? Okay? The reason I need to know that is because whatever the range is here, that's what we plug in there. Let me explain it a little bit differently. Composition kind of works this way. The inside function is like a little, the little factory thing going on here. So your domain numbers go in here. So your domain. So this is G. So I plug in an x, and G, which is x squared, acts on it. So it takes whatever x I plug in there, it squares it, and spits out the answer. So the range numbers are out here. This is range. This is what G of x is. This is your range, otherwise known as G of x. Well, then what do I do with that number? Well, right underneath it is the function f. These answers now become the domain of this. These answers go right from here, right into there. And this one does what? Well, it takes it and subtracts 1, right? Times it by 2 and subtracts 1. And then it spits out a new answer. Okay? So what I need to understand is, yes, is there any restrictions going into this one? But I also need to know what comes out because I have to match the out values from this to what I can plug into here. Now, the beauty of what we have in this one is every number works in this one. I can plug in any number into this. I have no problems. When I square it, I'm only going to get 0 and above. I'm not going to get any negative numbers. So no negative numbers anymore. Okay? But what can I plug into this one? Well, I can plug in every number I want. There's no restrictions on this one either. So it doesn't matter what goes into it. It was fine. So that means since I can plug in all the real numbers to this one, and this one will accept all real numbers, then my final answer will have all real numbers also. So the domain of this is also going to be all real numbers. It is not always that way. We have to walk through it. I'm going to show you some illustrations of ones that are not, and I'll show you why in just a moment. But that's what composition is. Okay? So, when you do domain, you find the range, you find the domain of each individual piece. Might be beneficial, to also do the range of the inside one, whatever one's on the inside. So I'm going to turn this over. I'm going to do another example. Keep that in mind. Here's a new F and G. This time F is going to be, this one, by the way, is number 19 in our homework list. It's not a homework problem, I think, but it's in the same grouping. And then G is going to be this one. And I want to find F of G of X. Now, mathematically, this shouldn't be that difficult. So let's go through the process and see if we can figure this out. G is the inside function, so this is going to be F of G, which is the square root of 1 minus x squared. The function F is here's my template, my rule. It's something squared, so I put something squared, just like that, and then I plug in this G into it. So plug that in, and then plug it in again into the other function. I have a square root that is squared, so they offset each other, and I get 1 minus x squared. That is the composition. Now, if I just looked at that, I would think, well, it's a parabola. I can plug in every number. And that's misleading, because this function was created by composition of these two functions. And these two functions had a domain to start off with. The domain of F, we already know, is just all real numbers. But this has a square root. So what is the domain of G? That is our question. To find the domain, I have to understand the nature of a square root function, which is that quantity can never be negative. That quantity must be greater than or equal to 0. Move things around. I can basically add the x squared to both sides, and I'll get 1 is greater than or equal to x squared. If you look at a number line, it will help you see this. If you want to flip it back around, you can. If you like looking at it this way, it means that right there. You can also solve for x. That's plus or minus the square root of 1, which is plus or minus 1. So that means on our number line, we have a negative 1 and a positive 1, and there's my regions. These are when it's 0. Right? I want this to be greater than or equal to 0. Well, at these two values, it is 0. So which regions satisfy this? So if I take this number right here, which is 0, and plug it in, 0 squared is 0. Is 0 less than 1? And the answer is yes. That means since this point is a yes, then every point in here is yes. Any points I pick out here and I plug it in will be a no, so they're out. This is my domain. The domain of G is this region right here. It is when x is between 1 and negative 1. That is my domain. In interval notation, you can write it as like so. So the square brackets indicate that the endpoints are indeed included. That is my domain for G. So that's my restriction. before I even plug into remember G? We took G and we plugged it into F, right? So before I even did that, I had a restriction. So my domain starts at this. I can't magically get other X values that I plugged in. I plug into G first, remember? I plug into G first so that I can only plug in numbers between -1 and 1. That's the only thing I can plug into here. Then I'm going to get an answer, and that answer goes into F, which will take everything. So that's kind of what it means. So what's my domain for this final answer over here? It is 1 minus x squared, comma, the x is less than 1 and greater than or equal to -1. That is my domain, and that's what you need to write. So this is the actual complete answer here. When you have a restriction on a function, you have to identify it at the moment that you give the function. So you have to put the domain here so that people understand what that means, if it's not easily seen. So that's how that works. Obviously, a lot more examples need to be done with this, and some conversations will occur when you have issues, but that's the idea. Two things to watch out for is be careful of the notation, that other notation that they use. I recommend that if they use it, just switch it to this format. I think this makes more sense, but it's up to you. If you like the other one better, it's fine with me. And take your time, work on your domains, ask for help as needed.